Let's see for the first case, which is static circuit in time varying field. Okay, let's see, you have a closed circuit, all right, and then this closed circuit is placed inside the time varying magnetic field. So let's say the time varying field is going into these directions. So that means this circuit will produce the induced current, where this induced current will produce the B induced, which is try to oppose to the magnetic field that exists in these regions. So we want to determine where the direction of the current and as well as the direction of the VEMF. Right, so we can use this formula. The VEMF equal to negative M, the integration of del B over del T dot ds. So this is our field, magnetic field, and this one is the surface covered by this circuit, the loop. And we have negative indicate that the VEMF produced will always try to oppose to the field exists in these regions. So we see the example 1. Find the VAB produced across the bar, given that the magnetic field density is given by BT equal to negative A cos omega T Z. So from this expression, we know this is a time varying magnetic field. Okay, so it's equal to negative A cos omega T Z. So let's see Z in this direction. So the cross mean the field is going inside. And the VAB is here. Okay, so we can solve using this formula. The VEMF equal to negative M d flux over dt. So because this is only one loop, we consider only one loop, so the N is equal to 1. And then d flux is equal to dBt. So this is our magnetic field, and we have to do the differentiation with the time before we dot product with the surface involved. So we put only the B differentiation. Of course, we got a minus sin, and then the limit of integration dx dy. So from we go back to the figures. Okay, this is a x in this section, this is a y. So from 0 to a and 0 to b. So we have here from 0 to a and 0 to b, and this one is the solution for this differentiation. You got omega a sine omega t dx dy. Okay, this is the same direction z. So the final answer will be negative omega AB, the capital A sine omega t. This is a VEMF. So that means the induced current should be flowing in these directions. Next, we go to the moving circuit in static field. What happens if we have a static field? If we have a static field and we have a closed circuit, but the closed circuit is stationary, so it will not generate any induced current. But what happens if we start to move the circuit inside the time invariant magnetic field? It can still produce the induced current inside the circuit. So how can we analyze and prove it? Okay, so beginning from the formula of force, the force equal to the QU cross B. So we have the moving charge at a certain velocity, and then we cross product with the field. So we can see that the direction of the charge is perpendicular with the field, and then we know before this that the electric field is equal to F over Q. So we bring the Q to the left hand side, so F over Q, so is equal to U cross product with a B. This is a electric field. Okay, we can determine the field, the motion, and the induced EMF. Induced EMF, this is not EMT. The induced EMF by using the right hand rule. So your thumb is a motion, your index finger is a field, and the middle finger is a induced EMF. Alright, so this is a formula for VEMF equal to the closed integration of EM dot dl equal to the closed integration of U cross B dot dl. So the U cross B and dl should be in the same vectors. It should be the same vector, so the dot product will have a certain value. So basically what is a M here? M here is defined as a motional electric field intensity. So generated by the motion of the charged particle. So that's why we label as a M here. For example 2, find the VAB produced across the moving bar if the magnetic flux density is given by B equal to minus AZ. Alright, from this formula you can see that the B has a magnitude of negative A in the direction of Z. This is a time invariant magnetic field. Let's say you have the bar. The bar is moving towards the direction of Y. So the magnitude is U and the direction is Y. So we have to find what is the VAB here on the moving bar only. Alright, so we can use the formula of VEMF equal to the closed integration of EM dot dl, and then the EM is U cross B. So the U is in the direction of Y and the B in the direction of Z. So we put inside the formula the VEMF equal to negative L UY cos minus AZ dot dx in the direction of X. The dx this is the direction of X, the dl. Alright, so Y cross negative Z, we got negative X. So we got negative AUX dxx. So the limit from 0 to A. And here, why we put negative? Because the original formula has no negative. And then why we put negative here? Because the limit is always opposite direction to the direction of the current. So let's say the current moving in these directions, okay, because the VAB is in this direction, so the current is moving like this, okay. So the limit is opposite to the direction of current, so the limit should be A to 0. If the limit is from A to 0, no need to put negative here, because here we put 0 to A, so we need to put negative. Okay, that's the reasons. So the VEMF equal to positive AU. Small a and capital AU. So that means the direction is correct lah. The direction of VMF is correct as labeled here. And the third case is a moving circuit in time varying field. So it's almost the same thing, but it just we move the circuit and we have the time varying field. So it's quite easy because it's just a combination of the first and second case. So the formula for VEMF is basically equal to negative the integration, the surface integration of del B over del T dot ds, and plus the closed integration of LEM dot dl. Okay, this is the expression for the third case. Let's see example 3. A conducting bar can slide freely over two conducting rails as shown below. Calculate the induced voltage in the bar if the bar slides at a velocity of u equal to 20 y meter per second and bt equal to 4 cos 10 power 6t minus y z milli Weber per meter square. So basically this is our figure. Okay, we have two conductor rail parallel with y-axis, and then we have a slide that can move freely from here to here along y directions. So that is the situation. And then we have basically the time varying field. Okay, we have time varying field, and at the same time it has a moving bar. So it's just a combination of two cases, which is the cases of a time varying field, and second case is a uh, moving circuit. So to solve this solution, we have to combine the first case with the second case. So let's solve this first case. Okay, right. Now we have the del B over del T, and the ds is basically dx dy. So the negative sign show the Lenz's law. Right, so we have this is our B. We have to differentiate with a del T, and then our dx dy. So the limit is from 0 to y. For y and x is 0.06. Why we have y here? Because when the slide moving, so it is moved at a certain y. This is the coordinate or distance, certain y, because it's moving. So we leave it as y, and when you solve this, you got the final answer to be negative 480 sine 10 power 6t minus y over 2 sine y over 2. So basically this solution by using the trigonometry identity of these solutions. Okay, this is just mathematics. And then after you solve this first case, you have to move to the second case. But from here, we can see that our VEMF for the first solution is negative, so that means our label of our VEMF and also the direction of current should be reversed. Okay. Next, for the second case, you have the integration of u cos b dot dl. Our dl is basically dx. Okay, our slide. So along the x direction, so dx in direction of x. Because we label our current from here to here, so the limit should be opposite to the direction of current, which is from 0.06 to 0. So that means we have to use the limit from 0.06 to 0, okay, along the dx, because we use the opposite direction of our induced currents. When you solve this problem later on, you got your answer to be negative 2. How you solve it? We have here we have the y cos z. So y cos z, you got x, right? But this is from bigger to small, you got finally the negative value. So again, here the VMF should be the opposite with what we label. As additional note here, case 1 is much bigger compared to case 2. So therefore, the VEMF is mostly contributed by case 1. So the case 2 is not really affected